Good evening and welcome to my YouTube channel. Welcome to the second session of our class today of basic electricity. Alright, if you're new here, you can do well for us and yourself to subscribe to this YouTube channel by clicking on the subscription button and turn on the notification so that you receive notification whenever we drop a new video or a new tutorial here. Alright, today we're talking about DC parallel circuit. A parallel circuit is formed when two or more resistances are placed in a circuit side by side so that current can flow through more than one path. Alright, let me give us a simple illustration where two resistors are placed side by side. First of all, we'll have a voltage source as usual. If you remember from our last class, the longest side is the anode, that's the positive, while the negative side is smaller, that's the cathode. Alright, this goes this way, goes this way, goes this way. Pardon my sketch. Alright, this is R1 and this is R2, where this is the direction of flow and this is as well the direction of flow of current in the circuit. So to determine the total resistances when two resistors are of equal value in a parallel circuit, we use this formula below, where you remember we say the total resistance is RT. So when they are placed in parallel, now we treated series earlier, when they are placed in series, note when the resistors are placed in series with equal value, that means R1 and R2 are of the same value, we use this formula where the value of here would be the value of any one of the resistors that's if R1 is equals to, the condition here is let R1 equals to R2 n value. So this formula now will hold all over number of resistors. So when R1 is equal to R2 in value, this formula is used to calculate the total resistances of the resistors in parallel. Alright, in the following illustration, I would give us a 15 ohms resistors so that we can calculate the total resistances. So let's take an example. Okay, let's just use this particular illustration. Let's say let R1 comma R2 is equals to 15 ohms. So when it's equals to 15 ohms, this formula we say it holds. So let's say R total now will be equal to the value of any one of the resistors. This means that either the 15 ohms here or the 15 ohms here would be picked. So we'll have this 15 all over. How many resistors do we have? We have two resistors, which will be equal to 7.5 ohms. Always remember the value as we spoke about it in our last class. Always keep the value in mind. So that's that for that. So what if we have resistors whereby R1 and R2 are not of the same value? How do we go about that? Let's take an example. Let's say the value of R1 and R2 now are not equal. This formula is equal value of resistors. That's 4 equal values of resistor. Alright, this second formula now, R, let's take RT. Okay, let's just divide this here. Let's say RT, when the resistors are not of equal value, we would have this formula now holding. 1 over RT is equals to 1 over R1 plus, let's say the resistors now are R3. Let's add it up here. Let's just draw a new circuit. I believe it will be better than just using that. I have a space here. Let's just take it, let it be more than 2. Let's take it to be 3 resistors now, so that you would understand what I'm trying to do here. Let's make it 3. This is always cathode, this is the anode, positive as always. So this is R1, this is R2, this is R3. Always remember, this is our voltage source. This is our voltage source. And direction of flow, let's say, is this way. Direction of flow is this way of the current. Alright, now let's say we have this case scenario now. It will be plus 1 over R2 plus 1 over R3. Thus, when the value of our resistors are not equal, keep that in mind. So let's give each of those resistors value, so that we can put it into calculation, so that you would understand. Let's say R1 is equal to, 5 ohms, and let's say R2 is equal to 10 ohms, and let's say R3 is now equal to 20 ohms. So how do we go about this? So this would be 1 over RT will be equal to 1 over 5 R1, but that's for R1. 1 over, it will be 1 over 10 for R2 plus 1 over 20 for R3. Always keep that in mind. This is the inserted values of the resistors. So what do we do now? It's easy. We find the common denominator, which we would say 1 over R3. Let's write it down. What we do here is find the lowest common denominator. So what's that? Here, for me, I would go for 20. I hope you're understanding what I'm saying. 20. Alright, let's do it this way. 20. 5 into 20 would be 4, right? And then 10 into 20 would be what? 10 into 20. Let's go back again. 5 into 20 is 4. 4 times 1 is 4. And then 10 into 20 is 2. 2 times 1 is 2. Plus 20 into 20 is 1. 1 times 1 is still 1. So here we say 1 over RT is equal to 4 plus 2, 6 plus 1 is 7, all over 20. So what do we do now? We've added the numerators. What do we do now? We invert both sides of the equation. And how do we invert that? By inverting both sides of the equation, we would have RT is equal to RT over 1 is still RT, right? Which is equal to 20 over 7. Therefore, our total now is equal to what? 2.8 0.86 ohms. So that is how we go about that. As you can see, we now have it in this pattern. So the second formula to use when there are only two resistors now. Okay, let's now go back to this case. So this case, the second formula to use when there are only two resistors and the two resistors are not of equal values. How do we go about it when there are only two resistors? Let's go and see to that. Let's see to that now. Alright, let's clear that. Let's clear that. Alright, so the second formula used when there are only two resistors in parallel. So let's take an example that this is the voltage source, as we said, this and this, okay, this is negative, this is positive, this is V, this is R1 and this is R2. So what's the R2 when the two values and there are only two resistors? The second formula to use is R1 plus R2 all over. No, here is multiplication all over R1 plus R2. That's what we use. Alright, in the following illustration, we would have two resistors as I've shown, each of different values. So in parallel we said of different values, right? Different values. That means here in this case now, R1 is not equal to R2. We use this formula, and R1 is, we use this formula. So let's say R1 is equal to, let's say R1 is equal to 5 ohms and then R2 is equal to 10 ohms. So R2 till now, as we said, when the two resistors are not of the same values, would be 5 multiplied by 10 all over 5 plus 10. 5 multiplied by 10 all over 5 plus 10. So what do we have here? We would have here as 50 all over 15. So when you divide that, you have RT is equal to 3.33 ohms. That would be our final answer. Alright, let's now talk about something peculiar. Let's talk about something peculiar. We'll be diving into more deeper stuffs today, so just stay focused. Let's now talk about voltage in a parallel circuit. If you can remember, in our previous class we talked about current. Now we're talking about voltage. When resistors are placed in parallel across a voltage source, the voltage is the same across each resistors. In the following illustration, now I would show you three resistors which are placed in parallel across a 12-volt battery. Each resistor has 12 volts available for it. So we would have a voltage source, remember, anode and cathode, negative and positive. we would have this. And we would have this. Let's make the resistors to be 3 so that you would understand more. Let's say this is R1, this is R2, and this is R3, and here V is equals to 12 volts. So we said when the resistors are placed across a parallel voltage source, the voltage is the same across each resistors. So when you measure the voltage here with a voltmeter across R1, the voltage will remain at 12. Same here, when you measure it, the voltage across this resistor would be 12 volts, would constantly be 12 volts. And when you measure it here, the voltage will still be 12 volts. I hope you are understanding what I'm doing here. It would be the same. So now what about current in a parallel circuit? Current flowing through a parallel circuit divides and flows through each branch in a circuit. So let's talk about now current in a parallel circuit. We've talked about voltage here. Now we're talking about current in a parallel circuit. And here we would have this circuit to consider. I just want you to understand the basics before we dive much into calculation, because what we're doing now is just the periphery. It's just scratching the top before we now dive in deeper. Pardon my sketch. I just want you to understand R1 to R3. So current now I total IT is flowing in, and is flowing when it comes towards this branch of I1 flowing in. When it comes to this branch here, we will have I2 flowing in. When it comes to this branch, we would have I3 flowing in. So the total current in a parallel circuit is equal to the sum of currents in each branch. Let me repeat myself again. The total current in a parallel circuit is equal to the sum of current in each branch. So this means that IT now here would be equal to I1 plus I2 plus I3. That will be the sum of the total current flowing in the circuit. Okay, let's now talk about current flowing with equal current flow with equal values of resistors in a parallel circuit. When current flow through a circuit in parallel and the value of the resistors are equal, what happens? Let's now look into that. What are we now looking into? Let's say current flow with equal value of resistors in a parallel circuit. So when equal resistances are placed in a parallel circuit, opposition to the flow is the same in each branch. Let me repeat myself again. When equal resistances are placed in a parallel circuit, opposition to current flow is the same in each branch. Now, in the following circuit I will draw, we would have R1 and R2 of the same value. So now, if the total current I total is 10 amps, then 5 amps would flow through R1 and then 5 amps will flow through R2. So let's draw it and see what I'm trying to explain. Let's have this. This is R1, this is R2. Let's say this is I total, which is equals to 10 amp flowing in. I total flowing in is 10 amps. So I said earlier, when equal resistances are placed in a parallel circuit, opposition to the current flow is the same in each branch. Alright, keep that in mind as we go. This would be I1 flowing this way, 5 amps. This is I2 flowing in, would be 5 amps. So what was I trying to say? I said if the total current IT is 10 amps, then 5 amps would flow through R1, and then 5 amps will flow through R2. That means I total is equals to I1 plus I2. IT is equals to 5 amps plus 5 amps. IT is equal to 10 amps, right? I hope we're going and you're understanding what I'm trying to say here. That's just it. That's just what I want to explain to you there. Alright, let's now dive into another case scenario where current flows. Now, current flows, note, in this first case, current flows through equal values of resistors in a parallel circuit. So the next case scenario here is, this is case 1. Let's label it as case 1. So let's have this as case 2. We say current flow with unequal value resistors when the resistors are not of the same value in a parallel circuit. Hope you're understanding. We would still maintain this equation, or rather drawing, still maintain this drawing or sketch, sorry. Still maintain this negative, positive. This is R1, this is R2. Here we have, let's say, all are 12 volt source. All these are 12 volts current voltage source. IT. Alright, we now have this sketch as this. When unequal resistors are placed in parallel circuit, opposition to current flow is not the same in every circuit. The opposition of current flow is not the same in every circuit. That means the opposition of flow in I1 circuit will not be the same in I2 circuit. So let's assume let R1 is equal to, let R1 be 40 ohms and R2 be 20 ohms. So opposition, you see the values are different. R1 is 40 ohms, R2 is 20 ohms. That means the opposition of current flow will not be the same. So what do we do to find the opposition of current flow in each or respective circuits? That's in the branch for I1 and the branch for I2. Alright, Let me explain something before we go further. As you can see, the resistor R1 is greater in value than R2. So current is greater through the path of less resistance. That means in R2, much current will flow in R2 compared to R1 because the resistance R1 offers is greater than that R2 offers to the flow of current. So that means much current will flow in R2 compared to R1. I hope you're understanding. Small values of resistances mean less opposition to the flow of current, and in the same manner, more current will flow in R2 than R1. So what do we do? What do we do to find the current flowing in each of those branches, in I1 and in I2? Remember our triangle before? We had a triangle in our first class as this, where V is here, IR is here, and we said if each of the parameter you want to play with, you just cycle it out, and if it is R you're looking for, you cycle it out, you get V over I. If it is I, you cycle it, you get V over R, and if it is V, you cycle it, you get IR. Alright, so what are we now looking for? Let's now calculate for I1. To calculate for I1, the branch of I1, we're looking for the current there. I, we say, is what? If we're looking for I, using this triangle, what do we have left? We would have V over R. So I1 is equal to V, our voltage source, over the value of resistor in the branch R1, which is equal to, we have 12 volt all over, what is the value of resistor there? 12 volt. No, let's make this for much easier calculation. Let's make this case 120 volts so that we'll just play around it easily. 120 all over, what's the value of R1? We say R1 is 40. Is that making sense? 120 divided by 40, we would have 0.3 amps. That's the amount of current flowing through I1. Here now we would have 0.3 amps. So in the case of I2 is equal to, what's the case? Same thing as V over R2 now is equal to 120 all over 20, which is equal to what? 120 divided by 20, we would have 0.6. Am I right? 0.6 amps. I hope I'm getting that clear to you. Sorry, there's a big mistake here. It's supposed to be, I don't know why I'm getting it this way. It's supposed to be 3.0, not 0.3. And the same way, this would be 6.0 amps. 6.0 amps here. Alright, so you can see this is 3.0 amps flowing, 3.0, and here would be what? 6.0 amps flowing. So as you can see here, much current flows through R2 compared to R1, as we have earlier stated before. So how do we get our I equivalent, I total? I total is equals to I1 plus I2, still the same case as it is in when the value of resistors are equal. We still find the total current as the same, in the same way, which is equals to 3.0 plus 6.0, which is equal to what? Equals to 9 amps. So the total current flowing in is 9 amperes. Is 9 amperes. Alright, I haven't gotten that. How do we calculate the total resistance? The total resistance is what we are now looking for. So let's now proceed. Let me clear some space. Pardon me for doing this. I would have to reduce some things so that we would have much space. Alright, let's redraw our circuit. This as this. Let's draw it more neatly. This is R1, R2, and we said R1 is equals to 40 ohms, R2 is equals to 20 ohms, and we said earlier that I1 here flowing this way is 3 amps, and this flowing this way is 6 amps, and IT is here, and 120 volts is here. So, and we said I total here was 9 amperes. So what are we now calculating? We're now calculating the total resistance. If you remember, these resistors are not of equal value. If you remember, we say RT for resistors that are not of equal value in ohms. So R1 times R2 all over R1 plus R2, which is equal to 40 ohms times 20 ohms all over 40 ohms plus 20 ohms, which is equals to 800 ohms over 60 ohms, which is equal to 13.33 ohms. That unit has to be there. So to prove that we have gotten our answer right here, 9 correctly, we go by IT is equal to what? The total value. We've gotten our RT as this, 13.33. To prove that we're right, we just say we would just say 120 all over 13.33. If you do that, you would get 9 amperes. So it means we are correct. So what else can we look into this evening? I want us to look at series parallel circuits. Another thing I want us to look at is series parallel circuits. Series parallel circuits. Series parallel circuits are also known as compound circuits. They're also known as what? Compound circuits. They're also known as compound circuits. And take this into your mind. At least 3 resistors are required to form a series parallel circuit. At least 3 resistors are required to form a series parallel circuit or a compound circuit. Okay, what's a series parallel circuit? Series parallel circuit. Let me just give you an illustration of what it means. And remember, put it in mind, we need at least 3 resistors to make a series parallel circuit. positive, negative. So this is what we call a series parallel circuit. Series, this is series, this is parallel circuit. All right, let's have this. Let's say this is R1, this is well, let's say this is R3, this is then R1, and this is R2. And let's say R1 is equal to 10 ohms and R2 is equal to 10 ohms as well, and R3 is equal to 10 ohms as well. I hope you're getting what I'm trying to do here. So what do I want us to do? I want us to find the value of the total resistances, total resistances. The formulas required for solving current, voltage, and resistance problem have already been defined before. So to solve a series parallel circuit, we reduce the compound circuit to its simplest form. And how do we do that? How do we reduce it to from complex to a simple form? How do we reduce it? We reduce it in this way. First, we use the formula to determine the total resistance in parallel to find the total resistance. So for this one in parallel, R1 and R2, what do? We find the total resistance is, say, R, which is equal to, if you remember, we said the value of one resistors in parallel, they are of the same value. So here would be value of any one resistor all over number of resistors. So here R is equal to what? 10 ohms. 10 ohms over 2, which is equals to 5 ohms. So I said earlier that we would have to reduce the compound circuit to a simple circuit. So we will now redraw the circuit, having known the total resistance of those resistors in parallel. Now reduce it to this form. This is what we now have. This would now be R3. So R1 plus R2 is equal to R3. We can still call this R3 if we like. Say 10 ohms here, 5 ohms here. We calculated this as 5 ohms, if you can remember here, 5 ohms. So what do we do next? These resistors are now in series. So R total now would be R3 plus R3, which is equals to 15 ohms. That is that for today. Or we can say that is that for that particular circuit, if you can understand it. Okay, if you wouldn't mind, I would like to reduce another one, if you're okay with it, simplifying a series parallel circuit to a parallel circuit. Let's try another example. Let's say the next example is just about simplifying a series parallel circuit to a normal parallel circuit, or that means simplifying a compound circuit to a simple circuit. you can say it in that manner as well. So let's have this example. So we have this here. R3,